Okay, in this problem, I'd like to take a look at the conservation of energy applied to a kinetic and elastic situation here. So imagine I have a block here that is sliding along. Maybe it's like a hockey puck or something. We'll call this surface frictionless for now to keep it simple. So I have a block sliding along with some velocity of, let's say, 4 meters per second. Well, this block has some energy. It would have taken some work to get this thing moving. Somebody maybe pushed it with some force. That work would have contributed to the energy of this block. What kind of energy did it have? Well, since it's moving, it has what we call kinetic energy. Kinetic comes from the word kinema, where we get the word cinema, which implies motion. Kinetic energy is all about motion. And how much kinetic energy an object has will be 1/2 times its mass times the velocity squared. So we can see here we've got 1/2 2 times 4 squared. We have 16 joules of kinetic energy in this sliding block. And as it slides along, if the surface is frictionless, then no work is done to slow it down, so it would keep on going indefinitely. But pretend this block collides with a system where there's a spring here. This spring is just sitting at its rest position. As the block collides with it, it's going to compress this spring some. What if we wanted to know how far does the spring compress? What is this distance from where the block collides with it to where the block comes to rest? Well, we would call that distance x. And how do I know how to do that? Well, we have kinetic energy here. You'll remember from our last video that elastic things can store up elastic potential energy. So we might call this UE. And recall that the energy stored in an elastic system depends on this equation, 1/2 K. K is the spring constant. Basically, it's the stiffness of the spring. If K is a big number, the spring is very difficult to compress or stretch. If K is a small number, then K will easily compress or stretch. 1/2 K x squared. X is the distance that the spring has been either compressed or stretched. Notice it starts here, it compresses here. It's not the whole length of the spring, just the compression distance here. So, how do I know what to do here? Well, let's give this thing a number. Let's say that the spring constant here is 10 newtons per meter. How far will the spring compress? Well, I can say when this block is sliding, it has kinetic energy. When it strikes the spring, it will continue to move, so it won't lose all of its kinetic energy until it comes to stop. When it stops at some distance x from the collision point, it will have no more kinetic energy. So I can say that the energy here turned into elastic potential energy. And recall, this goes back to the concept of conservation of energy. Whatever change in kinetic there is, plus whatever change in gravitational potential there is, plus whatever change in elastic potential there is, plus any work, this has to equal 0. Well, this is a fairly simple situation. Let's assume that if this is a frictionless surface, that there is no work done to friction. And I don't see any change in height here. This thing might have some gravitational potential energy. Maybe it's sitting up on a table or something like that. But the delta UG, the change in gravitational potential energy, is 0. Whatever energy it has at the beginning is the same energy it has when the spring has been compressed. So there is no change in gravitational potential energy. So I look here, what is the change in kinetic? Well, it was moving, and then it comes to a stop. So it will have a negative change in kinetic. And the elastic potential energy begins with 0, but as it gets compressed, it gains elastic energy. So there will be a positive elastic potential energy. So we can see if these things are 0, then I see that the energy gained by the spring is equal to the energy lost in kinetic energy. So I can simply say that UE equals the initial kinetic energy. I happen to know that the initial kinetic energy was 16, but just to show you how you can do this without numbers, I can substitute in for u my equation here, 1/2 kx squared. I can substitute in for k the equation for kinetic energy, 1/2 mv squared. Sometimes it's helpful to write out the algebraic expressions without putting numbers in, instead of just putting in 16 for k here. Sometimes it's helpful to do this. You can see things cancel here, like these halves cancel, and you can get a general form for this scenario. So with those halves canceling, if I want to know x, I have this becomes kx squared equals mv squared. Solving for x, mv squared over k. So this is by no means a general equation that works for everything, but for this scenario where kinetic energy is turning into elastic potential energy, to find the stretch or compression distance, I can simply use this expression. So I can put in my numbers now. The mass is 2, my velocity is 4 squared, and my k value is 10. Okay. If I'm doing this on a calculator, I might say 4 squared, of course, is 16. 16 times 2 is 32. 32 divided by 10 is 3.2. And the square root of 3.2, 1.78. I'll call that a compression of 1.8 meters. So there it is. If the spring constant has if the spring has a stiffness of 10 newtons per meter, and if this 2 kilogram slab is sliding along at 4 meters per second, it will compress the spring 1.8 meters. Now, that's usually enough. Our 16 joules of kinetic energy became 16 joules of elastic potential. But if we follow that up with what happens after the collision, it's moving, it compresses the spring, now it stops, but it won't stay there. That won't be its equilibrium position. This spring will unleash that elastic potential energy to launch this block sliding backwards. The spring will lose its 16 joules of elastic potential energy, and the block will get back its 16 joules of kinetic energy. Now pretend that sometime later this block is now sliding back somewhere else, and it has its 16 joules of 16 joules of kinetic energy. How much work is required to stop it? Maybe it encounters some rough surface here, like some sandpaper or something. As the block encounters this rough surface, from where it encounters it to where it stops, work is being done. The work done to stop it will be the force of friction times the distance through which it acts. So if this is 16 joules, and if I have, let's say, a force of 2 newtons acting back on it, how far will the block slide? If the force is 2 newtons, to do 16 joules of work to stop this block, it would need to slide 8 meters to do that. So the work needed to stop it would also be 16 joules, which may be 2 times 8 force times distance there. So we see again this principle that work done changes energy. When you walk up the stairs, you're doing work and you're gaining gravitational potential energy. When you throw something, you do work and you change the kinetic energy of the system.